and, DocuSigns and, M1 Finance.
ready to go. So,
Yeah, no, it's.
all right. Well, good to see everybody tonight. This is my first CJUG in person since the pandemic. So it's been a while. Yeah. So this is our, I think, for the whole CJUG organization, this is our second meetup ever since the pandemic in person. So good to see people in person again. And tonight we're going to have, is it Gerrit or Gerrit? Gerrit give a talk on JVM startup. But before we do, just wanted to square a few things away. Tonight we got a raffle for 2 JetBrains complimentary licenses. If you've won a license from us in the last 9 months, then you're not eligible to participate. Otherwise, we'll put your name in the raffle, and there will be 2 lucky winners tonight. CJUG continues to stand with Ukraine. We have a few links. We've got the Chicago Tech Slack. That's the Slack where we also announce some of our events. It's also a great way to be connected with a lot of the Chicago techies, not just in the Java space, but in just tech in general. And then for current Java news, there's Java Off Heap. It's a podcast run by some of our previous CJUG leaders. It's one of my favorite podcasts to listen to. Also, I'm sure all of you probably already got here because of the link for Meetup, but just in case, we are on meetup.com/ChicagoJug. This is where we currently announce all of our upcoming events. We're also on Twitter with the handle @CJUG. We also have a channel on Discord where you can engage with speakers before and after the meetings. This is an additional way to communicate with one another. We actually create channels for the individual events. That way you could like pick up on a previously left off conversation, which is really cool. And unlike Slack, you don't get that 10,000 message limit where it's like, oh, we're sorry, that message from 6 months ago, yeah, it's gone. Discord thankfully does not do that. Also, there's devitjobs.us. We are a community partner. We're currently planning for the next meetup in November. We're looking into doing something called a full-length unmeetup. So something less structured. We'll see how that goes. Also, I've heard that we have some more guest speakers in the pipeline, including Venkat. So it should be fun. If you're interested in speaking, please submit your proposals to present@cjug.org, and we would definitely be happy to put you under consideration. There's another jobs board. This is on LinkedIn. I think most, if not all of you, are probably on it already. And just some quick logistics. So for the photography and videography disclaimer, we're recording this session. And I think the Zoom meeting is also showing a video. So if you do not wish to be in the video, please let me or Che know right away. And just gotta put up those disclaimers. Also, we will be uploading the video to YouTube, as a replayable video later. So if you don't want that on YouTube, please let us know. I think we'll be all right. And all right, our gold level sponsor is JFrog. And we also have another sponsor tonight, and that is Project 44. Project 44 has been very generous to give us this office this evening, as well as the pizza and the drinks. So thank you very much. And AJ is here to share about Project 44. And then after that, then Gerrit will take it away.
Again, everybody welcome. Project 44 is a company that a lot of the products that we design and build is dedicated in the supply chain and logistics industry, right? At the end of the day, we are a SaaS company. We build products that really revolve around visibility, right? Visibility is something that we have all become to expect, right? I mean, Amazon has changed the game, Uber has changed the game, and with that, we all know that supply chain is pretty broken, right? We are seeing it every day as the prices for our groceries go up and everything else, and that is because it is a little bit more of an archaic industry. Project 44 is what I would consider a Generation 2 SaaS logistics company. The Generation 1 SaaS companies within logistics came out about 20 years ago. And that was a lot of how do we bring technology into this space where a lot of people don't use technology. We're talking about truck drivers, we're talking about warehousing facilities, all these other areas, because each one of these, in my opinion, is a node, right? And we want to connect all the nodes. The more nodes that we connect, the more dense a platform becomes, and the more visibility that it creates, and the more opportunity that it creates for everybody involved. And so it's really kind of interesting because with the visibility, it does create a win for companies to find those streamlined abilities to get their products to where they need to be, find customers that they can work with to enhance, because it eventually drives their cost down. When it drives their cost down, it drives our cost down. I think we've all gone to the grocery store recently, and a bag of groceries used to cost $50. Now it seems to cost $100, right? And so as we continue to grow and as we connect more pieces of that puzzle and more nodes, what it really does is it connects customers, right? And so the neat thing here at Project 44, a lot of the technology that we do use, it's open source, right? And so from a development standpoint, you're seeing a lot of Java, JavaScript, Spring Boot, React Native, a lot of those kind of technologies. From a DevOps point of view, the DevOps team is here working with a lot of great tools and technology to really drive home the ability for software engineers to deliver code to production at any time, right? To build those templates, to build those frameworks, to empower engineers to really be able to do what they like to do and not kind of get caught up in the rest, right? And as I look for, say, quality engineers, I really want to build something like the Semian Army, like Netflix has created, right? I mean, that is one hell of an impressive quality engineering group. I mean, think about it. I mean, they created what, Spinnaker with Google, right? I think those two kind of came together, because think about it, when something new drops on Netflix, you might have 100 million users watching the new Batman. Like 10 years ago, that was undoable to have that many people to stream that much video content at the same time. We are adopting a lot of those kind of technologies because of the amount of data that we do need to pull in to create these updates for our customers, because eventually it will continue to streamline their processes and it will give them the ability to, lower their costs, create the visibility so they're not losing money in all these different ways. So it's a pretty impressive start. We're about 8 years old, a little bit of history on our, technology journey. We started building with a lot of open source. In the beginning, it was we let products be customers and customers be products, right? We needed to learn, we needed to bring people in. And we all know that when you deal with big customers, eventually they'll say, we'll sign up with you, but we don't want these 4 features. Build us these 8 features, right? And we want them right now. And so over the past 3 months, Project 44 has come out and said, we're a product and engineering company. And what that means to me is companies no longer can say that to us. They can't say, we're going to buy only if you do X. We're still going to listen to our customers, but we're going to make sure that that ability or that they want to create can be scaled, right? Recently we have acquired 4 or 5 different companies, and we did our research to make sure that they're working with similar tech stacks, similar cloud providers and all that. But you all here know that we can't just drop these things together. They build their own connectors and they all run smooth, right? So there's a lot of work being done from design systems and engineering to make sure that if we've got our 38 products out in the market and they all have payment functionality, it's not 37 different payment functionality pieces, right? It's going to be something that's a little bit more unified, something more scalable. And that's where we start to find a lot more wins. That's where we can drive a lot more things home. And that's where the engineers come in, right? It's pretty impressive what y'all can do. And so with that being said, I will put my information up on the board if people are open to looking at new opportunities. I recruit on all engineering, all data, and that goes from open source to Python. So we've got data science, data engineering, software engineering. We really do have a little bit more defined at front and back end, but we're not going to sit here and say that's all you can do, right? We understand that a great engineer, to be a true engineer, you got to understand what's up and downstream, how one piece affects the other, so we can really kind of build amazing software. And so as we kind of continue into the future, we're looking for very passionate folks. We're looking for engineers. We're looking for builders. We're only 8 years old, which means we've got a lot of building left to do, which means there's a lot of greenfield space. There's a lot of learning that can be done. So, with that, like I said, I'll put my email address up on the backboard there. And if anyone wants to reach out, I cover all product design, and engineering. So with that, I'll turn it back over and we'll get going.
Cool. So anything I have to do here to get out of that?
You can just exit.
All right. And here we go. Okay. First of all, cool that I'm here. Cool that you do in person again. Because in the US it seems to be quite difficult at these times to get people meet up together. We had a conference here 2 weeks ago, JConf, and it was only 250 people showing up. We had to cancel 4 workshops from 5 on one day, and it was a little bit disappointing. So I have to say, we counted on 800, and then 250 showed up. So it's really strange. In Europe, it's totally different. But okay, it's cool. We are here. I will talk about CRaC, not the drug, but hopefully I get you hooked on that. So it's coordinated restore checkpoint in the JVM. Shortly about me. My name is Gerrit Grunwald. I work for Azure as a developer advocate. My background is physics. I studied physics and worked for the nanotechnology research and semiconductor industry for 10 years, and then slowly found my way into software development, and then now I'm here. So that should be enough about me. I'm also leading a Java user group, Java champion, and all these things that are not that important. Okay, if you would like to have the slides, they are here, so you can find them. It's not the version that I have here, it's a little bit older, but I update them nearly every time I give the presentation. So, but if you would like to have them afterwards, I can also provide the PDF or something. Okay, so Java is great. So first of all, who's working with Java here? And it's cool, because we have this vibrant community, as we see. We have hundreds of Java user groups, and we have thousands of free open source software projects. But the real great thing about Java is the JVM. That's the main thing that makes it all happen. The question is, how does the JVM work? And I bet all of you know better than me, but still, I will give you a very easy intro and only on a very specific part that's important for the CRaC project. So if you start with the Java source code file, then you put that into Java C, and we get this, oh, that was too fast, we get this cross-platform file out there, which is what's happening, which is a class file, which contains the bytecode. If you have a JVM on whatever platform, and you have a class file, it will run on that platform, right? So and then it gets into the class loader, which looks here pretty easy, but it's more complex, but we don't talk about class loaders here. So it gets from there into JVM memory, and from JVM memory, finally, it gets in the so-called execution engine. And the execution engine, it contains more than one part, but it has 5. If we take a closer look, then we have the interpreter, and then we have the C1 JIT compiler, formerly known as client compiler, and then the C2 JIT compiler, that was the formerly known server compiler. Who remembers that? Server and client compiler stuff. Remember someone? Not? Okay. Okay.
RMI? They had a lot of that stuff. Server.
Yeah, I mean, in the past, before Java 8, even before Java 7, you can choose between the compiler that you would like to use, server or client. The reason was that if you create a desktop application, then you probably use the client compiler. And the reason for that, I will come to that in a minute. So then we have the profiler and the garbage collector, but this is not interesting. We're just looking at these 3 parts, because that's important for the whole thing, how the code will be compiled. So the first thing that happens is the interpreter takes the code line by line and converts that into the instruction set of the CPU. And the JVM is watching that, and it's counting method calls, right? And if it reaches a specific threshold, then it will take this code, this method, and will pass it forward to the C1 JIT compiler. And then the C1 JIT compiler, it does really, as fast as possible, compile the stuff without a lot of optimizations. I would say nearly no optimizations at all. And the reason for that is, I told you, that's the formerly known client compiler. And on a desktop, if you double-click an icon, you would like to software should just pop up, and you don't want to wait until the compiler really has the perfect code, right? So it just should just run. So that means it compiles the code as quickly as possible with low optimizations. And then again, the JVM is watching this compiled code, and it's again counting how often is this code called. And if there's another threshold, let's say 10,000 times the code was called, then it takes this code and forwards it to the C2 compiler, including profiling information. And then the C2 compiler, which is the formerly known server compiler, this is much more complex, and it really takes longer and compiles the code slower, but really a lot of optimizations are going on there, right? And the reason is, if you remember the monolith time when we had the application servers, it doesn't really matter if the server took a minute to start up, right? It wasn't really a problem because it was running for a month or two, or it was really not the big deal. So that's the reason why time wasn't a problem here. Today, that's different. And this combination, that's called tiered compilation. And what we have this C1 and C2 compiler and the interpreter. And the interpreter is level 0, and then we have 3 levels for the C1 compiler, and then we have 1 level for the C2 compiler. This is not really important to know. It's just because you have then transitions between these levels, so it could be that some code will stay in interpreted mode all the time. It can also happen that it jumped from interpretation into C2. There are all these different ways how code can be transferred between these levels, but the preferred way is this. So we interpret it, then we get into C1, including the profile information, and then after some time it gets into C2, and then it's fully optimized. That's the preferred way of doing it. You can imagine if the C2 compiler, the queue for compiled code, if it's full, then the code will stay longer in C1 until the queue is empty, and then it can get code into C2. So these are all the different things, but these 3 levels we need for the next thing, which is the execution cycle. And this is in principle the same that I showed you before, just as a, let's say, closed loop. So that means we start with interpretation, which is slow, and then we profile that. And then it gets into C1, which creates very fast compiled code, not really high optimized. And then again, we profile that code. And then it gets into C2. And then there is this thing, and that is called de-optimization. So does anybody know what that means? Because that's quite interesting. I will come to that in a minute. You see that it closed the loop, that you can already see once it is here and we have de-optimization, and we start with this again, right? So this is an ongoing cycle. De-optimization, it's, if we just break it down very simple, and we have this code block, which just is an if-then clause. When we check if the value is greater than 0, then the result equals 3, otherwise it's 0. That's the main idea. That's pretty simple, just this if-then. If we profile the code and the profiler figures out, in 99% of all cases, it's always greater than 0, right? So that means nearly every time we have result equals 3. The compiler takes the code and reduces this whole block into this. It just says the result is 3. That's it. And it guards that in the JVM. It still does the check, is the value greater than 0, but not in the compiled code anymore. That's in a different area. That means instead of checking that every time, it just returns result equals 3. And that's pretty fast, as you can imagine. So if we now pass in a value that is 5, then it's true and the result is 3, everything's fine. But if we pass in a value equals 0, then this is not true anymore. Then this code block has to be just thrown away, right? And then this is de-optimization. Then it has to take the whole thing, interpretation, C1, C2 again, but then the whole block. And then this takes time. You can imagine this is a performance hit, right? So, and this is the optimization. And that happens, for example, if you have your application running and you apply some workload, and then the compiler sees the workload and see, okay, this part of the code is mainly used, so I optimize the code for this part. And then suddenly, after a day, something else happens in your application because it's used in a different way. And suddenly it has to throw away this block and recompiles everything. It's very dynamic, so the JVM can do that stuff, the JIT, right? That's the main advantage of having a just-in-time compiler. Okay, so that's all cool, but it takes time, as you can imagine. And if we take then a look, that leads me to JVM startup, and you probably, who's someone suffering from JVM startup time here? Someone works with lambdas? Because they really suffer from that. So the problem is if people talk about the JVM is so slow, startup time is so slow, then if you ask them, okay, what does it mean, startup time? And then probably most of the times people can't really explain what it means. It's really, there's no definition what is JVM startup time. People just say, the JVM starts up slow. Okay. If you take the Java file, just the main class, just system out print line, hello world, compile it and run it. It's blazingly fast. That's the JVM startup time. It's fast, right? The JVM itself doesn't take a long time. It's your code that takes some time. It's your application. And we define it as the time to first response of your code. That's the startup time. First time your application reacts on something and you get a response from it, then this whole thing, this time, that's the JVM startup. And then there are people that say, yeah, but you know, if you have high-speed trading companies, they shut down their systems in the evening and they start it up in the morning. And when they start it up in the morning, then the system should be hot. So that means the same state as it was in the evening. To do that, they start up the server not at 7 in the morning, they start it up at 3 and apply some workload for 4 hours to make it run again in the same state. That's what they do. This is JVM warm-up or application warm-up. So because what they do is they apply workload to the application and the compiler will compile and optimize the code for that workload. And people getting confused, what is JVM startup here, right? Is that the whole time? What is it, right? So we define JVM startup as time to first response, means the JVM will be loaded and initialized, optimizations going on. Then we load the application classes with all the dependencies and all that stuff, initialize the resources and some application logic, and always optimization. Optimization means this C1, C2 optimization stuff in the compilers. This is usually not what we define as JVM startup. But if you hear people that, oh yeah, we have to first fill all the caches, and then this is not startup, this is warm-up, right? So we really have to make this differentiation between these two things. And if we then take a look at the JVM performance graph, you see 3 colors here. We have yellow, green, and blue. And the yellow part, this is interpretation. And you see it's maybe in the 100 millisecond range. Because you think, oh, interpretation, that really takes some time. No, it doesn't. It's really fast in the beginning. And then it directly jumps into C1. And you see even C1 is, because it compiles fast, this is mainly compilation in C1 and interpretation. Yes, the yellow is interpreting. This is compilation and profiling. So, and then it starts getting into C2, right? And then you see the performance gets better and better over time. And this is then what we, let's say, the JVM startup time. And then you see these gaps. This is usually garbage collector process, right? Because then JVM stops everything. Heap will be cleaned and compacted, and everything will be cleaned up, and then it restarts. And so these are these, you see it's in the same frequency more or less. But then we see these things. And this is the optimizations. These are really bigger gaps. So the code was optimized, suddenly some branch went in the other direction, and the code has to be thrown away, recompiled, and everything takes some time. So these are the performance hits that we see here. This is the optimization. But at that point, usually the code is more or less fully optimized. Okay, that's cool, but you see it takes some time to do that. And if we now take this into a microservice environment in the cloud, then that means we run the first time the service, then we have to start it up, second time start it up, third time start it up, and so on. It's always, we have to run through the whole thing. And that's not really convenient for some things, not for everything, right? But if you have microservices, you would like to scale them out, then it really takes some time. It would be great if we can do something like that. We just run it once and warm it up, and then the second time we run it, it's just fast. That would be perfect, right? So we just start from here, continue running. That would be the ideal case. And then and so on and so on. Okay. Are there any solutions to do that? There is, first of all, class data sharing. Does anybody know what that is? CDS, app CDS, or dynamic CDS? Okay. This is there is application and dynamic CDS, and it dumps internal class representations into a file. So that means the JVM itself, when you start it up, it has to load the same classes all over the time, always the same classes. So you can load them, store the representation in a specific file so that it can load it from that file much faster than collecting it all over the place. The same goes for application CDS. If you have an application and you start it up and it has to collect the class files from all the dependencies, then it takes some time. If it does it once and store that into a file, then the next time you start it up, you can just take it from the file in an optimized way, right? That's the main idea of CDS. And you can share that on each JVM start. So if it was created once, the next time you start it, even another JVM can use that file because it's in a specific place on your hard drive. There's no optimization or hotspot detection in here, right? This is really just class loading time that will be improved here. But this can give you up to 1 to 2 seconds. It could be faster just by using that. And if you use Java 12 and above, then this is already default. So app CDS is enabled per default, but you can tune it. There is I had to put a QR code here. I just have a link. So there is if you look up this guy, Arnold Belozin, he has a good presentation about just CDS, and also on his blog, he has a very detailed blog article, how to tune CDS to get these results here. So you can really improve the speed of starting up your application by just using CDS. But as I said, it happens here on the class loading thing. It's not in the compiler, interpreter, and so on. It's really just loading classes faster. Okay, so that means it's nice to use that, but it doesn't help us with the ramp up of the JVM. Then there's ahead of time compilation, and I bet everybody heard about that. Is someone using here GraalVM native image in production? No, why not?
No good reason, I guess.
Okay.
Just experimenting.
Okay. Okay, so that means, why not using AOT? We don't have to interpret bytecodes there, right? And there's no analysis of hotspots. If we just talk about AOT. Then we have no runtime compilation of code, and we can start with full speed. It's a native image, which is great. And GraalVM native image does that. So that means, okay, that solves all our problems, right? So we just use that, and then we get rid of the startup problems. Well, not so fast, because our AOT is, by definition, it's static, and that means code is compiled before it is run. If you just use AOT, and it means the compiler has no idea what the code is really doing. So it just takes the code, compiles it, and that's it. And then there's something called profile-guided optimization. This is only available if we talk about GraalVM. It's only available in GraalVM Enterprise Edition. So if you have the Community Edition, you can't use PGO. And what it is GraalVM also comes with the JIT compiler. And what they do, they start it up when you use PGO. They start it up using the JIT and run your application. Then you apply some workload. They profile that and save that profile. And when they create the native image, they take the profile and apply it to the native image. So that means the native image gets all the stuff that was profiled. That's cool. The problem is you can't really touch every part of your code, right? That would take forever to do that. So that means you can optimize it for a specific case, and then it will work for that case pretty well. But if something changes, it can't react on that because the code is compiled already. So this is the reason it might not work for everything. If we take again a look at this performance graph, then it means if you use AOT, you can just plain AOT, it can get up to 60–65% of the JIT. It can be faster, it can be slower. It really depends on your code. There is no general rule. But if you use PGO, you can reach up to 90% of the JIT. Sometimes you can reach the JIT performance, but mainly, most of the times not. It really depends. This is not. There might be cases where you can reach 100% all the time. It really depends on your code, because what they do is they do extensive profiling in this PGO time when they do that, and also do a lot of optimizations there. So it can reach a really high speed. But like I said, this is really not flexible code at that moment. It's fixed code. Okay. And we need to profile it once to make that work. So if we do just a short comparison between AOT and JIT, then it means AOT, it has a limited use of method inlining because it can't do that at runtime, only before it runs using the profile, but otherwise there's no way to do that. And then we also have no runtime bytecode generation where the JIT can do that, of course. And reflection with CRaC, for example, is possible, but it's not easy because you need some kind of configurations, and the AOT approach needs to know the whole world. So that means I need to know every class that is touched, every line of code, because if I compile it into native code, then if I don't know it, it won't be part of the native code. That's the main reason, which is different. Right here, you can, in the JIT, you can use reflection whenever you like. You can also, at runtime, you can load code and execute that. In the AOT code, this is not possible. And you can't really use speculative optimizations. This is something that is, where the JVM is really good in that. So that means it monitors the code, and then it does stuff like branch prediction. So, okay, it looks like that if most of the times, this is the way we do it. So I optimize the code in that way. And then it's very fast in that way. But if that changes, it can be decompiled, like de-optimized, and then do in another direction. That's possible in the JIT, where the AOT can't. You can just do it at one, but if something changes, then it won't react on that. This is the difference. And the speculative optimizations, we figured out that this part is responsible for more than 50% of the performance of the JIT, because it really monitors the code when it's running and optimizes it aggressively. And with the AOT, this is just different. And that means the overall performance with the AOT approach is typically slower, and the JIT is typically faster, but it really depends. So the main disadvantage that I see is if you have AOT or native image code, then you run your code in the IDE, you run all your tests, and this is still Java, and all the tests are green. And then you create the native image, and it can fail, because native code is not Java code in the JVM. So that means the behavior of native code is different than Java code. And that means it's hard to really debug that stuff. So if you have, I had that thing that one guy after my session came to me and said, we have this problem. We have a code coverage, I don't know, 80%, and everything's green. But when we create a native image and we run it on a server, it crashes. We have no idea what to do. I also have no idea what to do. Sorry. This is the problem. If you have
I know. Start commenting out stuff until it works, and then you'll be good, and then go backwards.
Yeah. It's really it's tough, because here we are so used to, oh, I can debug that stuff. It's no problem, right? But in this case, you can't, because it's different. It's just one file, and it's a native file, and the Java compiler can't debug the native code. In IntelliJ, they are working on solutions, but this is still a problem. On the other hand, AOT code is just fast when it starts up, right? Where the JIT really, we saw that takes some time, and we have no overhead because it's compiled once in AOT native image, where the JIT compiles all the time. It's always compiling, especially at the startup. You have to compile all the code, and then we have this overhead. We see that peak and CPU usage, and also memory, that we don't have that with the AOT. But with the AOT, we have the build process will take longer, because there we have all the overhead, right? But you do that before you run it in production. And then we have a smaller memory footprint, because in the AOT native image, we only compile the code that we need. That means if you use some library, and in that library, you just use one class, then the AOT code will only compile this one class. Where in the JIT, you load the whole thing. Everything will be compiled. So it's just because, or at least interpreted, because it's loaded, so it's there. That means the memory that is needed is bigger than for the AOT approach. Okay, the main disadvantages here is for the JIT is it requires more time to start up. We have the CPU overhead to compile code at runtime, and we have a larger memory footprint.
I got a question. So in these days of the cloud, it's possible to get an instance with 32 CPUs, or these crazy amounts of CPUs. Does JIT compiler perform better with?
And that's exactly what companies do. They buy this really high number nodes, let's say with 32 nodes or with 32 CPU cores, to get rid of this peak in the beginning, to reduce the startup time. The JIT can handle that.
It works.
Yeah, it works. But the problem is it's expensive, because these nodes are really expensive. If they have the more cores, the more you pay. That's the main thing. But I will come to that, because this is one really advantage of the CRaC stuff, and we will see why. So, different approach. There is a project called CREO. I don't know if someone heard about that. It's a Linux project. It means checkpoint restore in user space. And checkpoint restore, just to explain that shortly, everybody's used to, if you finish work, you just close the lid, right? Next morning, you open it again and everything's there. This is checkpoint restore, exactly this. The operating system detects, oh, the lid is closed. I save everything I have to disk. Next time I start it up, I just load it back to memory. This is checkpoint restore, that's what it means. And this library, CREO, of this project, is a Linux project, and it's part of the kernel since 2013, so that means it's not really new. And it's more or less bulletproof, because it's used for a long time. And it was made to freeze a running container application on Linux, and then store the state of this checkpoint to the disk, and then in the future restore from that checkpoint back to memory. In principle, what I told you when you close the lid, this is exactly the same thing that the operating systems do. But this was made to do it with applications or containers. And it's already used. It's used by OpenVZ, by Docker container, by a Linux container, by Docker, by Podman. They use that. So that you might have even used it without knowing it. So, but it has some things that are important to know. So it's implemented in user space, and like I said, the main goal is migration of microservices, containers for microservices, and it relies on the proc file system on Linux. Not every Linux distribution uses proc. So that means if you don't have the proc file system, for those who don't know what it is, it's really just a folder in Linux, and this folder contains all the information of the system, of all the processes and everything that's going on. And CREO just uses the information in this folder, right? And it's called a file system. And it can checkpoint lots of things. So processes and threads and application memory, memory map files, shared memory, open files and pipes and FIFO sockets, inter-process communication channels, and it can also timers and signals, and it can restore a TCP connection from one side only, so without handshaking and all that. So it's quite impressive what is possible with this. And of course, it doesn't come without challenges. And one challenge is, as you can imagine, if I create a checkpoint on this machine, I take the file, put it on another machine, and restore it there, will probably not work. First of all, the problem is I run it on an x64 machine, and then I put it on an ARM64 machine. This will definitely not work, because a different architecture, it can't work. The other thing is, if you have an open file on one machine and you need that, and on the other machine it's not there, this file, then also this won't work. Or shared memory, of course, you can't use that because on the other machine you don't have it, right? The next thing is, if you would like to start it multiple times on the same machine, also it doesn't work, because on Linux we have a so-called PID, which is the process ID, which is unique. And this is also part of the checkpoint. So that also means, if you guess that if the PID is already taken by any other process, you can't restore from that checkpoint. That's reality. It means you can't just restore it once, second time it won't work, but even if you would like to restore it and the PID is already taken, then it won't work. This is the drawback here. We are working on a solution for that too. And now we come to the Java virtual machine, because I said you can checkpoint applications, and the JVM is more or less just an application that is running in Linux. So we should be able to checkpoint that and restore. And yes, that is possible. You can do that. But the problem is not really the JVM. The problem is your application in the JVM. Because the JVM is just like a framework where you run your application in. That means your application has the files open, has the internet connections, the database connections. And if we just now say from the operating system point, oh, checkpoint the JVM, it will do that. But the next time you restore, your application will continue to run, and suddenly the database connection is not there, the file is not open, so it will crash. Right? That's the problem. So it's not so easy to do that. And that leads me to CRaC. And the most important thing is this coordinated here, because this is exactly what we try to solve, this problem that the application needs to know when there was a checkpoint and when it was restored. So what we do is we patch the CRaC project to make it work with the JVM, and we bundle that with the JDK to make it available and make sure that always the right CRaC version is there. Because Linux comes with CRaC, and it might be a different version, and we have to make sure that it works. That sometimes leads also to problems, especially when you run it in a Docker environment. But still, it's possible, so we fixed that, but in an older version, that was a problem. We clean the heap and compact it, so it's in principle the same as it's done as you do a garbage collection. The same thing we do before we do it, so that means when we create a checkpoint, we make sure that the JVM is in a safe state by compacting and cleaning the heap. And we throw checkpoint exceptions, so that means if something goes wrong, this CRaC project will let you know that something went wrong. So it just won't continue. It will tell you, oh, wait a minute, there was an exception here, so you forgot something, right? And then we have a pretty simple API, we will come to that in a minute. And you can create checkpoints either using code or JCommand. Using code, in the first time you think about it, might sound a little bit strange. Why would I like to create a checkpoint in code? When I heard that the first time of that project that we did, then I thought, well, that's so cool. I can run my application and do checkpoints from time to time, and then I can just like do something like an undo, right? So something went wrong, and I can just say, oh, restore from the last one or from the one before the last one. That would be awesome, but yeah, it doesn't work like that. At the moment, when we create a checkpoint, the JVM will be shut down. So it really closes down the JVM. And we have also the idea to make that work so that you can create checkpoints and the application just keeps running. It would be good. Let's think about something like an undo functionality, or let's say you have something like that on your server and you do checkpoints every second. And suddenly you have a DOS attack. So that what you can do, if you figure out something goes wrong, you can just go back to the last checkpoint. So that means it won't really affect you, at least for some time. Of course, if it goes on, you have to do something. But you can at least get out of this sort of situation by doing that. It could be just one idea. Okay. And it uses JVM SafePoint, which is, like I said, it's the same thing that is used if you do a garbage collection, because the question often is, okay, if you stop this stuff and I have a multi-threaded application, how do you make sure that everything's in place correctly? The JVM can do that. Garbage collection works the same way. So you have no idea when the JVM does a garbage collection, it will also shut down all the threads and restart them. So you don't have to handle that. So that's the same here. So it's the same mechanism that is used. The project it's not, we do that from Azure. It's led by one of our engineers, Anton Kozlov, but it's an OpenJDK project. So that means it's not something that is only available from Azure. So it's public available in openjdk.org project/CRaC. And we try to make it available. So we provided the code. If it will ever become part of OpenJDK, it's not in our hands. This is Oracle's decision. And they might say no, because it's not available on Mac and Windows. But to be honest, I mean, I always ask who's running production server on Windows.
You.
People laughing, but I had a couple of times people say, yeah, we run production.
It's really cheap to run Windows VMs.
Well,
compared to Amazon Linux.
People do that, yeah. So, and with this, you can't use CRaC. This is just not possible. We have a library that we also provide, and I will give you also links to the GitHub repositories, that makes it possible to, it comes with dummy interfaces. So that means the library detects if the JVM supports CRaC, it makes use of CRaC. If it doesn't support CRaC, it will give you just the dummy interface and it does nothing. That means you can develop on Windows and Mac and won't crash. And as soon as you run it on Linux, it will run. So we can get around this problem that it will give you some exceptions like, oh, I don't find that in the JVM, I can't find the CRaC classes and stuff. So we have a fix for that. But even with this, it might be possible that Oracle says no, won't be part of OpenJDK. it's not in our hands. And if it won't happen, then we probably will build it in our own JVM, because we have also our own JVMs. Okay, but to come back to the point, so what we needed to do, we need to let the application, if it's running and we create a checkpoint, we need to let the application know, now you will be checkpointed at this point in time. And then we wait some time, and the next time we restore from that checkpoint, again, we have to let the application know, now you got to be restored, right? You have been restored from a checkpoint. The reason for that, and I come to that, is that you have to make sure that you can react on this circumstance that there was a checkpoint, because you have to close files and database connections and reopen them, you know, when we have a restore, right? This is your part. And we do that by command line parameters, which is -XX current CRaC checkpoint 2 equals, and then we pass a path to the JVM when we start our application. And then the JVM knows when we create a checkpoint, I store the checkpoint in this folder. That's the main idea. If you would like to restore from this checkpoint, then you just call Java and point it with this parameter to the same folder, and then it will recognize, oh, there is a checkpoint, I restore from there. That's the main idea. So this is the two things that we added to the command line parameters. And the API is pretty simple because it's only one interface. It's called resource and has two methods, before checkpoint and after restore, which is pretty simple. Like I already said, it's up to you to handle that. That sounds terrible because you have to change your code. But keep in mind, this is made for microservices. Microservices are not that big, shouldn't be, right? Should be microservices. And usually, if you have something like a database connection, then you have one class where you manage all that, like a database manager or something. This would be the class where you implement the interface. Then in this method, you would close the connection to the database, and in that method, you would just restore the connection to the database. That's the main idea. And the same goes for open files. If you have that, it's mainly all socket connections and files. That's what you have to take care about. Everything else is handled by the project. So the idea is you implement the interface, and then the JVM needs to know somehow where are all these resources, and then it needs to contact all these classes here, right? Like before and after restore. So this is done by a so-called context. It means you have the resource object where you implement this resource interface, and then you have to register them in the JVM, and that's done by this context. Right? And then if it's registered in the context, then the JVM can let you know and notify all these resources in case there's a checkpoint or there was a restore. You can get the context by the core get global context is a static method because you only have one context in the JVM because it needs to know all the resources that are running. And it looks like that. You implement the interface, then you get the core get global context, and then you register this resource in that context. That's how you do it. It's pretty simple, and you usually do that in the constructor. You register that. And then there's another thing to keep in mind. It might be the case that you have resources that depend on each other. So you have, for example, a database as a resource. And then you have other resources that make use of the database. So that means first the database has to be there, and then the other resource, right? So there's an order of how you register them. You decide the order by register them like, first of all, database is class A, and then there's the other resource, class B. So you make sure first you register class A, then you register class B. The reason for that is that this context, it maintains the list of all the resources, and it makes sure that it calls the before checkpoint methods in the reverse order as they have been registered. So that means you first register A and then B. When before checkpoint is called, it will call, first it will close B and then it will close A, call B. First B, then A, so in the reverse order. And then when we do the restore, then it's the same order that you use to register them. Because after the restore, everything should be the same as at the point where you start the JVM and the whole application. Right? So I have a demo that shows that a little bit better. Okay, I already told you that you can create a checkpoint in code. And this is a little bit misleading. We might change that because it says checkpoint restore. That was the reason why I thought, oh, great, I can at runtime create a checkpoint and restore, keep it running. No, this is really just creating the checkpoint and shut down the JVM. And the other thing is using jcommand. Okay. Now that leads me to this very simple example that should give you an idea how it works. So I just have a scheduled thread that every 5 seconds it will be executed. It will run a loop from 1 to 100,000 and create random numbers from 1 to 100,000. Then it will check if this random number is a prime. And it will use a cache. And the first thing it will do, it will check is the result true or false in the cache. If it's in the cache, it directly returns it. That's all in memory. This is blazingly fast because there's no calculation here, right? If it's not in the cache, then it has to calculate if it's prime. If it's a large number, then it will take longer, as we all know. And so that means we calculate, we get the result, we store it in the cache, and then we return it. So that's slower, probably. Okay, that's in principle, that's the whole code. And to make it more realistic, the cache will forget stuff after 10 seconds in this case, because that's what you usually do. The cache never keeps the stuff forever, right? So they time out, and if it's older than whatever time, then it will just wipe it out. And this is just to make it more realistic. This is the whole thing, pretty simple. That means the first time we run it, the cache is empty. We run it through the loop 100,000 times, random numbers, and then it has to calculate all the stuff. That means it's slow. And then with every iteration, it should be faster and faster because the cache will fill up slowly. And then if the cache is full, that means every result is in the cache. Nothing has to be calculated, so it should be fast. In principle, that should be the same as if you start up and optimize code. It's the same behavior, more or less. And I made a test on a different machine, and it looked like that. After 9 iterations, it started like, okay, now it leveled out. And this is because the cache started removing things, then it added things, and so on. So this is what you usually see in an application. Right? It's never flat. It's always like levels at a specific area. Okay. The demo, I have two. And the first thing is pretty easy because I just do all that in slides first, and then I can explain it. So I have this CRaC 4 jar, and I started with this command, and I pointed to the /CRaC-files folder. There it should store the checkpoint, right? And then I run it, and it will show me the pit, and then I just have some print lines here where in the classes where I say the first thing that I register is the generic cache, and the second thing that I register is the main class. These are the two classes where I implemented the interface. It's not needed in this, it's just for this example, right? In the classes, there's nothing that needs really be a resource. I just would like to make sure that you see, okay, this is the order I register them, and then the first run took 27 seconds on this machine. And then it's slow because the cache was not filled, and then we go on. Second run, third run, and we see it gets faster and faster and faster because the cache will be filled. And then at one point we reach a time where we say, okay, now it's fast enough. So that might be the time to create a checkpoint. And on the second shell window, I just call jcommand with the same jar file, and then jdk.checkpoint. This is the command to create the checkpoint. You can also use the pit. You don't have to use the jar, right? The pit might be easier. I could also put here jcommand 4240 jdk.checkpoint is the same. And usually you would use that, right? I just use the jar file in this case. Okay, and then what happens is the before checkpoint methods will be called, and you see it's the reverse order that I registered them, which makes sense. And then it will create the checkpoint, and then it will kill the JVM. So that means first it will call your methods. You can close all the resources. Then it will create the checkpoint, and then the JVM will shut down. That's the main idea. So, and this is the JVM warm-up in this case, because I fill the cache, right? But it's in principle the same as if you start up a JVM. Okay, now it's killed, and we wait some time. Yeah.
I'm sorry, I missed, when you, at that point you stop the JVM, what happens to your open files and your
You close them in this methods.
They're closing them.
You have to close, not the methods, you have to do that, right?
I have to do that.
You have to do that. Because we don't know what you're doing in your code. If you have a database connection, then we give you the opportunity in this method before checkpoint to close it. And then in the restore from checkpoint, you can, or after restore, you can reopen the connection.
So what if I forget to close it?
You will get a checkpoint exception.
Okay.
So it will let you know, and then it will fail, and it will tell you there was a checkpoint exception, and it will show you in which class it was, and then you can just fix it. So that's the main idea. Okay, now we waited some time, and I just called this command, just Java, and pointed to this folder where I stored the checkpoint, right? And now, if you listen to me, I told you that the cache will forget things every 10 seconds, right? Now I waited longer than 10 seconds. So what should happen now? The first time I hit the cache, it will check all the values and will filter all the stuff that is timed out, and it should be everything, because the stuff that was in the cache was stored at this checkpoint at that point in time. When I restore it and I take, let's say, system nanoseconds or something like that, it will figure out, oh, everything's timed out, and it will wipe out the cache. And it should start from here again, because then it should be empty, right? And this will happen. So what it means is, but here it won't. The reason for that is that I knew that this will happen. And what I did, because in the checkpoint, everything is stored, the whole JVM, the whole state. In the moment, in this method, before checkpoint, I just stored the system epoch milliseconds in a variable. Means this variable is in the checkpoint. When I restore it, I can get the current system epoch milliseconds and calculate the delta. Then I know the delta between the checkpoint and the restore, and then I can apply that delta to all values in the cache and make them valid again, right? So that's how I did it. That also means if you have data that is time dependent, it won't work directly, because this will time out. You have to take care about that. The question is, if you need to do that, it really depends on the microservices that you use, or let's say on the code that you use. Not every class needs to be checkpointed. It makes sense if you have services that are short-lived, you start it up, or that you have to scale out fast, then there it makes sense. The question is if this microservices contain time-dependent data, but if so, then you have to take care about that. So if you play around with this stuff and you stumble upon some problems related to this, oh, somehow it's not that fast as I thought it would be, then probably you handle something with time-dependent data, and then you have to take care about that. Just to keep that in mind, that can happen. So because it happened to me the first time I ran that, I ran it and I saw, it should be fast, and then it was slow again, and I figured out, because the time that is in the cache is the time from the checkpoint, and at that moment I restore it, it's already, everything's outdated, and it will be wiped out. Okay, and then it will keep running, and you see that the time here was 23 milliseconds to start it up, and the cache was already filled. Okay, so that's the thing. You create the checkpoint like I told you. Either you use the jar or the pit, or from code you use core checkpoint restore. So the question now is when to checkpoint, because that's not so easy to identify. Some companies have defined workloads that they use to warm up the JVM. For example, this high-speed trading companies, they do that. They have some set of workload that they apply to the JVM, and then everything's in place. But usually you don't have that. If you have something like a shop that's running, and it depends on how many people access your code, then you don't know, right? So you can't really warm it up. What you can do, what we do when we do the demos, is we run the application with a typical workload, and we use this parameter, which is -XX column plus print compilation. And what it does is when you add that by starting the application, it will print out all the compilations that are done by the compilers. It looks terrible in the shell because like you don't see anything. It's really just scrolling. But at one point, it will get slower and slower because then at some point everything's compiled, or most of the part. And that means this is a good point to create the checkpoint because now everything is perfectly compiled and optimized. So we are on top of the curve. So then you can create the checkpoint. That's how we do it when we create demos, because then we can see, okay, first of all, you see a lot of compiles going on, and then suddenly it ramps down and see, oh, now it's getting there. So we're getting to the point where everything is compiled and optimized. And then you can create the checkpoint. Right? This is just a hint how you can do it. Yeah.
Do you have any like anecdotal data on how long that might take for a service? Like, are we talking 10 minutes?
That
10
depends
hours?
completely on your service.
Okay.
So we have customers, Netflix, for example, is also a customer. We have a specific JVM, which is different from the OpenJDK one, where we have our own compiler and we have our own garbage collector, and we have also a different way of starting up the JVM. And we have customers, and this JVM can handle heaps up to 20 terabyte, so which is a lot. And we have customers that use that. It's incredible. You can imagine the machine, right? 20 terabyte of heap. And we have 0 garbage collection process with this JVM. And these guys, if you have to warm it up, it takes sometimes 2 days to warm up a JVM because it's such a huge code base that they run on that. But yeah, so it really depends. It could be seconds, it could be milliseconds, depends on what you do. It's really, this is something, and that's why I put in that slide. It's just to give you an idea. You have to play around with it. And this is a good indication. We are working on something to make it, to use this one internally, because we know how the JVM works and we hack into the JVM. So we try to add stuff to give you an idea, like a parameter that you can ask, and then, oh, now it's optimized, and then create a checkpoint. But we have to find a good metric that works everywhere. So this is a good indication. If most of the stuff is compiled, then it's good. But if you have a lot of decompilations going on, or stuff is loaded at runtime, then it will never stop to compile. You have to play around with it. But if you just do simple demos, then this works quite well. And you can try that on a very simple service, and even on the Hello World app, you can try that. And you see that, oh, compilations first is like, and then suddenly it drops, and you see, oh, now it's the point, everything's compiled. And that's pretty fast with a simple program. Okay. A typical use case for this stuff is, instead of running it on a bare machine, you run it in a Docker container. Right? That's what you usually do. And then you create the checkpoint in the Docker container. Then you store the state of this container, including the checkpoint. And then you can start it from this container, and it will always start from the checkpoint. That's the idea. The next question is, that's all cool, but how can I do that in a CI/CD system? And I don't have an answer yet, because I'm just currently working on a solution on how to make that work, for example, in GitHub Actions. The problem is that we need to have the checkpointed files in the container, and therefore you have to run it first, warm it up, some workload, and then create the checkpoint, and then store the state, and then use this one and deploy it to your server. That's the thing that we are working on to give you some idea. But at the moment, this is a little bit tricky, but you can do it manually, right? So I will show you a demo where I did that manually. And the compatibility, it's only available on Linux x64 at the moment. We can make it available on ARC64, so on ARM. But because we just build it from time to time, the JDKs, because it takes some time, at the moment it's only Linux x64. And then there is something, we call it upgrade and downgrade. So that means if you, for example, if you have the JVM and you have the compilers are really smart in the JVM. Because what they do is, they don't not even compile it for a specific CPU type, but also for the specific CPU family. So that means if you have a Core i7 stepping 1, then the code is different from Core i7 stepping 4. Or from a Core i9, it's again different. The code that is, it's all Intel, it's x64, that's fine, but each CPU has different possibilities, and the JVM makes use of that. That means if you compile it on a Core i7, it will work on a Core i9. But if you do it on a Core i9, it won't work on a Core i7. Right? So you have to keep that in mind. That's important if you run it in the cloud, and for example, you run it on Azure. Then you can create some kind of node groups. I think it's the next, oh yeah, and if you run in a Docker container, it will also work on Mac. So as long as you have the same architecture, like Core i7. So in Azure, for example, we have so-called groups of nodes, or node groups, and in Azure it's guaranteed, and in AWS it should be the same, that this node group has always the same CPU architecture. That means if it is in Core i7 stepping 4, then it will be for all nodes in that group. This is guaranteed. But if you run that then in a Kubernetes cluster, which can run different groups, right, at the same time, then you can run one group which has Core i7, the other one has Core i9. So you have to make sure that if you create something like that in Kubernetes, that you make sure that all the node groups that you use have the same CPU architecture. But then it will work. And like I said, I know that definitely from Azure, because I talked to the product manager, and in AWS I talked also to some guy, and he said yes, it should be. I don't have the definitely yes, but he said yeah, it should be. It wouldn't make sense to change that because it would lead to other problems too. Okay, so the demo code is available on my own private repository, and I just give it to you because it's easy to start with. So you can download the JDK, you can fork that project and just start it and it will run. So, and it's documented in the README how to do that, also how to create a Docker image and all that and run it in Docker.
It's not a 20 terabyte.
This is pretty simple, just 4 classes. It's the stuff that I showed you, right? Just loop and it just creates it's really simple stuff. But as a demo, it's quite good because it gives you an idea. And so the question is now, I told you, oh, we created the JVM and hacked the CRaC stuff into it, and I showed you a demo that I created, and of course everything worked great, right? So the question is, how good is it really? And of course, we did some tests with Spring Boot and Micronaut and Quarkus, and also some XML transform. And these are the time to first operation or time to first response for these different frameworks using plain OpenJDK. For Spring Boot, it was around 3.8 seconds. Or 9, and then Micronaut 1 second, Quarkus similar 980 milliseconds, and then XML transform took 4.3 seconds. Using CRaC, that was the startup time. That's really an improvement. And the interesting part here is that you see this took 4.3 seconds, and this took 1 second, but with CRaC it's nearly the same. And the reason for that is we only rely on I/O. We just load the stuff back into memory, and hard drives are fast. The only difference here is if you have a lot of resources where you have to restore connections to the database or stuff like that, that take a little bit longer, but even this is in the millisecond range. You will never get into seconds again. This is mainly loading, compiling, interpretation, and all that stuff. And you can reduce that using CRaC, and you get in the same range as the native image GradVM stuff. Plus, you keep the JIT. So the code is still completely able to optimize it, or the JVM is still able. The JVM doesn't really know that it was stopped and restored. So for the JVM, everything's, oh, I'm going on here, I don't know. So, and that makes it really powerful because you don't have to take care about stuff like, oh, because when I stop it and restore, should I do something? No, you just have to close the resources and restore them again, and that's all you need to do, and then it will work. That's for sure. And the summary is that CRaC is a way to pause and restore a JVM-based application, and it doesn't require the closed world. This is for the native image. They name it closed world because they need to know everything. We don't need to know. You can even, after a checkpoint, you can load code, and it will run because it's a JVM, it's a JIT. It can handle that. And the benefit is potentially extreme fast time to full performance level. It eliminates the need to identify hotspots and compile methods and recompile because we can do that before we create the checkpoint. And when everything's optimized, then we create the checkpoint. So there's no need to really check it again. And we have improved throughput. It's an OpenJDK project, and it can save infrastructure costs. And this is the point that you had with the 32 CPU cores, because the problem is what you usually see. This is CPU utilization. This is time. Then usually you see this peak in the beginning. That means suddenly all nodes are used, or all CPUs, or all cores. And this is the JVM startup time that we see. Because the application is already running in interpretation mode in the beginning. At the same time, it starts to compile stuff, right? And that means we have interpretation and compilation, so optimization overhead here. And then after a specific time, it levels out at some point, which is not 100%. It means if you buy this 32 CPU core node, which is really expensive, then you pay only for, I don't know, let's say the first 10 seconds. And after that, you might also work with a 16 core machine, a 16 because then you don't need all the power. It's just to make the startup time really faster. That's the main reason why companies do that. So that means if we create the checkpoint here and start from there, you can really save money, but because we don't have to have this startup time there. So it can reduce infrastructure costs, definitely. It really depends. So if you have a problem with startup times and you have this high amount of CPU cores, just to reduce it, then it will definitely help you reducing costs here and the CPU overhead. Still, the memory footprint is bigger than with GraalVM native image. Okay, so the whole stuff, also the demos with Spring Boot and Micronaut and Quarkus are available at github.com/CRaC. And in this repository, you will also find the JDK, and we will update it from time to time. You can download the JDK there, and then you can either use the demos that we have there, or if you would like to play around with my demo, then you can fork it from my repository. Right. Okay, there's also a wiki, OpenJDK, but this is not really very informative. So you'll find more information on in the GitHub repository. That leads me to the real demo, because this is the same that I showed you before, but this time I will run it in a Docker container. So what I did, and yeah, I just let me go here, and I'm not in the image. So I created a Docker image, and in that, or a Docker container, and in that Docker container, I copied the jar file, then I logged into the container, started the stuff, and then with the second shell, I logged into the same container, I created the checkpoint, then I saved the state in a specific container, and now I start the stuff without using the checkpoint, right? So I just start the Docker container here, and it doesn't work because I didn't start Docker yet. I have to start that first. Then it will work. Take some time to start it up. Yes, so nice. Come on. And that's funny because I told you this is only Linux, but because it's the same architecture, and that is a Core i9 machine, and I created that on a Core i7 machine, and you can just run it. It works, which is really great because before that it didn't work in a Docker container from the beginning. I had to have a virtual machine on this one and run it in Linux, and it was always a hassle, but since last week it works. So now I started, and you see, okay, we see the PID is 1 because it's in the container, nothing else is running. And you see the JVM startup time is 80 milliseconds because there's a JMX bean that gives you the JVM startup time, and it's fast. The JVM itself is fast, but you see the code, 28 seconds, I guess that's usually the time it takes because the cache is empty and so on. So we have to warm it up. We have to run through all these things, and then now we see 28 seconds, then it's around 11, and then 4, 1, and then after that it's fast. Take some time. Come on, yeah, 10, nearly 11, and then it should be 4. Yeah. And now, yeah, now it sees, okay, now it gets every 5 seconds, it will run through the cache. You see the cache is nearly filled completely, so it's fast. It's always the same. It's fast now, but it took some time to get there, right? Now I start the container with the checkpoint, and here we go. And you see, I took the checkpoint at iteration 17, and it continues counting. And the good thing is I can start the same thing in another container here. All right, so, and it's just fast. So it really starts up pretty fast. And the most of the time that it takes here is to start Docker. It also takes a couple of, I don't know exactly, depends, but it's in the millisecond range to start it up. And now if I stop it, I can restart it again, and it will start again from 18. So this is the big advantage. And you can now imagine if you create this Docker container and then you can really deploy that, and you can scale out in the cloud very fast because the startup time it's really in the millisecond range. And this is the same. It takes a little bit longer if you have stuff like Spring Boot or Quarkus, but it's still in the 30 milliseconds. And it depends on the nodes, of course. This one is not the fastest computer. It's my old MacBook Pro because it's an x64. But on the M1, unfortunately, I can't run it there. But it's much faster there. So it really depends. And yeah, and that's it for this session. So that's all I have to show you. And I hope you get an idea what you can do with CRaC.
It's good, but when's Windows coming?
Good question. Yeah.
So the files that it generates pretty large.
No, it depends, of course, on the heap, because it has to save the heap. And for this demo, it's 30 megabytes. And I have no numbers for the other demos that we did. But it's you can imagine if you have a large heap, then the files will be bigger. And it's for this one, it's if I remember right, it was around 30 files, I think. But we have one big file which contains the heap and everything, and then it's a lot of small files. And it sums up to 31 megabytes for this demo. And this is binary stuff that is stored there. And this is done by CRaC. So that means I check the files because you can see them, and I would like to see, is there some clear text in there, right? It's nothing, it's just binary code. And of course, it's hard to dig into that, that's for sure. But it's not specifically encrypted by us or something, because we use CRaC to do that. And the interesting part is, because it's running on Linux and it uses the PIT, so that means the process, that means everything that is related to the process will be checkpointed. That also means if your JVM uses off-heap memory, which usually you can't really do, right? You can do it in the JVM, but you can't really think about how should I checkpoint that, because it's not part of the heap, it's off-heap. So you can do that because it relies on that PIT and it's part of the process. Everything that's related to the process will be part of the checkpoint. So it's quite interesting to see that. Yeah, like I said, it's if you do that demo, you can also run the jar on your machine. If you have a Linux machine, you don't have to run it in Docker. Then you will see it should be around 31 megabytes. Check the files and take a look into it. It helps you, but it didn't help. So, any other question? Yeah.
How would you go about like scrubbing secrets or something, passwords or sensitive information?
Yeah, that's what I mean. If you just have the files from the checkpoint, there's no clear text in there, so you won't find it. Right? So I did the test, so I tried to find some text that I used somewhere, but because everything's compiled, this is compiled code, you won't really find it. And you can, of course, do that if you know the source code, right? And then if you get for specific, or let's say you have access to the source code and you have access to the files, then you might be able to figure that out. But it's in your Docker container, so it's nothing that is accessible to someone to get to these files easily. So it usually, this is usually made for short-lived microservices. They live for a couple of minutes and then you throw them away and then you spin up a new one. So usually that shouldn't be a problem. And there is a problem when you use CRaC on the operating system level on your own, because it's just a command. You can use CRaC and you can point it to the application and it will create the checkpoint. In this case, you can. There are ways how to get to the information if you have access to the machine. But because we bundle it, and it's a specific version of CRaC that is patched by us, so you can't really do that because it's somewhere in the JVM. So I can't really give you a number there and say it's absolutely because we don't have any experience yet. So we just found that this is an interesting project that you can use to stop and restore a JVM. And the results are really interesting. It's really fast. And IBM does exactly the same. They use it, they have an OpenJ9 JVM. It's another compiler that they did. And they have a project which is more or less the same. They have also an API, and it looks a little bit different. It's called Instant On. It's the same thing. So they do the same. If you use, for example, Semaru, which is the IBM JDK, the current one, then you can use Instant On there. Just exactly the same thing. Any other question? If not, you can also ping me on Twitter, and that's the only social media service.
What's the name of the IBM one? I was looking at that at work.
It's Instant On is the name, and it's in Semaru. That's the actual JDK that they have. I'm not sure if it's in the official one or but if you look for OpenJ9 instant on, you should find it. There are also sessions about it, and it's pretty much the same. It's just because they don't have before checkpoint and after restore, they have something like, I think it's checkpoint hook and restore hook or something. It's very similar what they have. And they have also some other parameters. It works a little bit different. So this is a more convenient way of doing it. It's at least the stuff that I saw was a little bit more scientific, the way IBM does it. So you need to really know command line parameters and all that. So where here you just have to implement the interface and you can do it. There's a little bit different in the IBM way of doing it, but it's the same idea. They also use Creo. It's the same thing. And there are other projects that do the same on Linux. So Creo is just the oldest one and the best working one with the most features, but there are other projects in Linux that do exactly the same, checkpoint restore, and we could use them. So it's abstracted in the JVM, so we're not really relying on Creo. Because if there would be something on Mac or Windows, we should be able to do that in the same way, but there isn't. Nothing available. Creo is also not available on Mac. So yeah, but with Docker you can at least run it on a Mac, which is no problem. I mean, I've never tried to run it. This Docker container might even run on Windows. Why not? It should. I don't have a Windows machine, but at home I have one, so I will try that. It should work. If you have the same architecture, then it should probably work also on Windows. And did someone ever run a Linux Docker container on Windows? I never did that. Does it work? I don't know. I can imagine it would work because in principle it's just you need just the same architecture of the CPU to make that work. And if it both is on Intel x64, then I guess it would also work on Windows. And this is what you usually do. You run it in a container. You don't really run the jar file plain on the machine. Usually it's a container. Okay. If there are no other questions, then we are done. And like I said, it would be awesome if you can play around with it. It's a GitHub project. You can find issues. You can ask questions. We are totally rely on that because we just came up with the idea, made some tests, but as you can see, we have not the applications to use it, right? We have just idea how you can use it. And usually we get the ideas from sessions like this. So yesterday I was in Baltimore and have a session there, and there have been people from the government, from all that secret government stuff, and they had totally crazy ideas. How to hack machines using CRaC and all that. I was like, oh, what? What's that? Yeah, this is great. We can do that. Okay. How to take over a machine using CRaC, and yeah, they would like to really. It was really interesting. Oh, well, we can use a checkpoint, and then we can put it into a machine. If it supports CRaC, then we can take over the machine with our code. And it's like, okay, yeah, okay. That was the first thing they came up with. I just thought about restoring it to make it faster. Oh, you can. Oh, they had really crazy ideas. Yep. Yeah, but this is that's why we do that. I just travel around and try to get people hooked on that stuff and try it out. And if you have feedback, then we really would love to hear it. It's because you know your code better than we do, and you know the problems that you run into. So if you have problems, then just file issues, and we will try to answer them. And that's it.
Thank you.
Well, before we call it a night,